Hi, in this video, we will learn how to solve the non-homogeneous part for the second order ODE by using the method of variation of parameters. Previously, we have learned the method of undetermined coefficient to solve the second order ODE. But there is one limitation for this method, which is the right hand side must be in the format of exponential, sine, cos, or the polynomial function. If the right hand side function is no longer in this format, then we can consider to use the method of variation of parameters to solve the problem. For example, if you have complicated right hand side functions such as tangent, log, and so on, so we cannot use the previous method to solve it. And in this case, the method of variation of parameters are still applicable. So this is the step to implement this method. First of all, you need to arrange the equation in the standard format like this, where the coefficient for the second order derivative here is equal to 1. In the second step, you need to let the right hand side function here equal to 0 to form the homogeneous ODE. By doing this, you continue to solve the complementary solution, which is in this format. So we have learned this before. In the third step, you can find the particular solution by using this formula. y1 and y2 here are obtained previously in the complementary solution. So you can substitute. u1x and u2x can be computed by using this integration, where the Rx is equal to the right hand side function in the standard ODE format here. y2 and y1 are obtained in the complementary solution here previously. Lastly, W here means the Wronskian, which can be computed by using this formula. Previously, you have learned how to use the Wronskian to check whether y1 and y2 they are linearly dependent or not. If the Wronskian is equal to 0, then we say y1 and y2 they are linearly dependent. If the Wronskian is not equal to 0, then in this case, y1 and y2 are linearly independent. So after you compute using this formula, you can obtain the W. So once you solve this integration, you should obtain the u1 and u2. And then after you substitute inside this formula, then you can obtain the particular solution. So the total solution will be equal to the complementary solution plus the particular solution. This is the final solution to this second order ODE. The drawback of this method is that it is time consuming to compute the integration for some function. So if the function here is very complicated, so in some cases we cannot solve it using the analytical solution, and you might need the numerical integration to solve it. In this example, we have second order ODE where you want to solve the y with respect to x. So based on the right hand side, the function is complicated and it cannot be solved by using the previous method of undetermined coefficient. So in this case, we can use the method of variation of parameters to solve it. In the first step, we will solve the homogeneous part first by let the right hand side equal to 0. So in this case, we convert it to the characteristic equation where the y double prime become m squared, y prime become m, and y become 1. After solving this characteristic equation, you obtain the root equal to -1 for m1 and m2. Therefore, this is repeated root case. From here, you can obtain the first solution to be exponential -x. To avoid linearly dependent solution, you need to multiply the independent variable to the exponential -x here. So your independent variable is x in this case. Therefore, substitute the x inside. So this is your y1 and y2. Then you can find the complementary solution equal to the constant 1 multiplied with y1 plus constant 2 multiplied with y2. From the y1 and y2, we can use it to find the Wronskian. Substitute the y1 equal to exponential -x inside, and then you differentiate it to obtain this answer. Continue to substitute the y2 inside and differentiate it, and you obtain this answer. Then you continue to compute the determinant by multiplying this to obtain this component minus with the multiplication between these two components. After you do the calculation, you see this term can be cancelled with this term. Therefore, you only have exponential negative 2x. In the second step, we will focus to solve the non-homogeneous part in order to obtain the particular solution. And you know that the particular solution is equal to u1 y1 plus u2 y2, where the u1 can be computed by using this formula. So you can substitute the right hand side function equal to this here. Then your y2 is equal to this here. Lastly, your w will be equal to this. So after you substitute, you compute the integration, you should be able to obtain this result. You can refer to the mathematics note to find the detailed procedure to solve the integration here. We continue to find the u2, which can be computed by using this integration. So you substitute the right hand side function equal to this, and then y1 is this, and w is from here. And then after you perform the integration, you should be able to obtain this answer. So we can continue to find the particular solution now by using this formula. So you substitute the u1 from here, u2 from here, y1 here, and this is your y2. So after you substitute, you should obtain this. Then you can continue to collect the coefficient for the ln x exponential negative x. So over here you also have the ln x exponential negative x, which give you x squared. So x squared minus with x squared divided by 2 give you x squared over 2 ln x exponential negative x. Lastly, you collect the term from the exponential negative x. So this is the coefficient, and this is another coefficient. So 1 over 4 minus with 1 give you negative 3 over 4. You have success to compute the yc and yp, so we can combine it to obtain the total solution. So this is your complementary solution add with the particular solution. And this is the final solution to this second order ODE. In this example, you have second order ODE where the right side function is complicated that cannot be solved by the previous method of undetermined coefficient. So we need to use the method of variation of parameters to solve it. So in the first step, we will focus on the homogeneous part by let the right hand side equal to 0. So we can form the characteristic equation and find the root. So root 1 and root 2 m1 m2 equal to 1. So you have repeated root case. So you can find the y1 equal to exponential x, and your y2 cannot be equal to exponential x because these two will be linearly dependent. Therefore, you need to perform the treatment by multiply it with the independent variable x here. So this is your y1 and y2, and we combine it in such a linear combination, which is called the superposition. So this is the final format for your complementary solution. So after you obtain the y1 and y2, you can continue to find the Wronskian. So by performing this calculation where you take the differentiation of your y1 to obtain the y1 prime, and this is your y2. So after you take the differentiation, you obtain the y2 prime to be this. And then you continue to perform the determinant. Take the multiplication of these two elements, you obtain this component minus with these two components. Then after you do the simplification, you should obtain the Wronskian equal to exponential 2x. Then we continue with the non-homogeneous part where the right hand side is equal to the exponential x divided by x squared plus 1. So the particular solution is given in this formula, and you need to find the u1 and u2. u1, u2 can be computed by using this formula. So you can see you need to integrate for the Rx function. So Rx function is the right hand side function here. So this is the right hand side function also. So y2 and y1 can be computed from the complementary solution here. In this case, your y1 is equal to exponential x, and your y2 is equal to this. So you can substitute it inside. Lastly, you substitute the w equal to exponential 2x inside the w here. So after you perform the integration, you should obtain the U1 and U2. You can refer to the engineering mathematics note for the detailed procedure of this integration. Then you success to obtain the U1, U2 and the Y1, Y2. So after you substitute, you should obtain this. After you simplify it further, so this is the final answer for your particular solution. Lastly, don't forget to combine the complementary solution and the particular solution to obtain the total solution. And this is the final answer for the second order ODE here.